Hi everyone, welcome to this lecture on forecast evaluation. My name is Sam Allen. I'm a postdoc in statistics at the Karlsruhe Institute of Technology. First of all, why do we evaluate weather forecasts? Well, the reason for making weather forecasts in the first place is that we assume forecasts will provide us with some useful information that we can use for things like decision making and risk assessment. But in order for our forecast to be useful for these purposes, it's important that we have a rough idea about how good the forecasts are. And this raises an important question, namely, what does it mean for a forecast to be good? And at first, this might seem like a fairly trivial question. A weather forecast is good if it is in some sense close to the weather that we actually observe. For example, if I say that the temperature tomorrow will be, say, 20 degrees at a certain location, then this forecast is good if the temperature at this location is indeed close to 20 degrees. But of course, in reality, we generally don't just predict one weather variable at one point in time and space. We instead predict multiple weather variables simultaneously at multiple points in time over an entire spatial domain, such as Europe, or more generally, the entire globe. And in addition to this, we generally don't just have point forecasts issued by, say, deterministic weather models, but we often have probabilistic forecasts in the form of ensembles. And in this case, we're essentially trying to compare a collection or ensemble of highly structured, high-dimensional possible weather scenarios to a corresponding observation. And in this sense, what does it mean for a forecast to be close to the observed weather? And this is, of course, important because often we want to compare two different forecast models. How can we say that one forecast is better than another if we can't measure closeness between a forecast and an observation? And of course, we know that objectively, one forecast model is generally not better than another. It may be the case that one forecast performs better than another with respect to some respects, and another forecast performs better in other respects. And so in this sense, the general goal of forecast evaluation is to provide a thorough understanding of how our forecasts behave and how they perform. And we can then use this information not only to compare two different forecasts, but also more generally to learn about systematic biases and systematic errors that occur in the forecasts. And we can then remove this from our models to result in more accurate and more improved forecasts in the future. And so with this in mind, the structure of this talk is as follows. I will first talk about metrics that we can use to compare two different forecasts. And these metrics typically condense forecast performance into a single numerical value with which we can rank different forecasts or forecast models. And this includes scoring functions and scoring rules. And I'll additionally talk about how we can use weighted scoring rules to target more extreme events during evaluation. But also other evaluation metrics that don't just focus on one forecast and observation, such as metrics based on contingency tables or the anomaly correlation coefficient, and also spatial verification metrics. And we can evaluate two forecasts using some evaluation metric, but there's no guarantee that the forecast that results in the best score or the best metric is actually any good. And in particular, if we're using our forecasts for things like decision making and risk assessment, we additionally need that our forecasts are reliable or calibrated. And so I'll additionally talk about methods we can use to assess whether forecasts are calibrated. And this typically comes in the form of graphical diagnostic tools such as reliability diagrams and rank histograms. And these two sections focus more on the statistical methodology used to evaluate forecasts. And I should say that this is a lot of material to cover in a fairly short space of time, and so I'll really just give a very surface-level introduction to these concepts. But I'll then finish off by talking a bit about the practical challenges that arise when evaluating weather forecasts, and in particular when we want to evaluate AI-based or data-driven weather models. So firstly, suppose that you want to compare two forecasts. Now, as I've said, we typically do this by summarizing forecast performance into a single numerical value, and we can then plot this value for different forecast models as a function of time or as a function of space. And this allows us to understand whether one forecast performs in some sense better than another for different points in time and space. And these metrics are often calculated using what we call scoring functions and scoring rules. Scoring functions are generally used to evaluate point forecasts. So a point forecast is just a single possible outcome, such as the output of a deterministic weather model. The scoring functions essentially measure the distance between a single forecast and a single observation. And of course, in practice, we have access not just to one forecast and observation, but to several from each of the different models. And we generally evaluate forecasts by looking at the mean score or the average score over all of these multiple forecast cases. And because we're interpreting the score as a kind of distance between a forecast and an observation, we adopt the convention that the lower score results in a more accurate forecast. And arguably the most obvious example of this is the squared error. And of course, if we take the average of this over many forecast cases, then we have the mean squared error, or if we take the square root, the root mean squared error. And the squared error is just one example. Another popular example is the absolute error and the corresponding mean absolute error. And just as scoring functions allow us to evaluate point forecasts, we can use scoring rules to evaluate probabilistic forecasts. And a probabilistic forecast is a distribution of possible outcomes. And of course, in weather and climate forecasting, probabilistic forecasts typically come in the form of ensemble forecasts of possible weather conditions. But the premise is exactly the same. Scoring rules quantify the distance between a single probabilistic forecast and a corresponding observation. And in practice, we calculate the mean or the average score over multiple forecast cases. And we can do this for multiple forecast models, and then we prefer the model with the lowest score. And so the general idea is that we take a probabilistic forecast or ensemble forecast, we take a corresponding observation, and then we want to summarize the forecast performance into one value, with which we can then compare competing forecasts. And if we evaluate forecasts using scoring rules, it's important that our scoring rules are proper. And a proper scoring rule is a scoring rule that is minimized on average or an expectation by the true data generating process. And what this means is that if we know the process underlying the weather or the observations that we see, then we are encouraged to issue this as our forecast because no other forecast will receive as good a score on average or an expectation. And I should say as well that there is an equivalent of proper scoring rules for scoring functions when evaluating point forecasts. In particular, we want our scoring functions to be consistent for a given function. And this is often neglected in practice, but I should say that the theory of consistent scoring functions is just as important as the theory of proper scoring rules. And why do we want our scoring rules to be proper or our scoring functions to be consistent? Well, as I said, proper scoring rules satisfy the property that the true data generating process receives the best average score. Now, I would argue that if we are comparing two different forecasts, this is something that we want our forecast valuation metrics to satisfy, because this data generating process is essentially what we are trying to forecast. And so if we receive a better score than this data generating process, then it becomes difficult to interpret what this score really means. And if we're trying to compare two forecasts based on this score, then this comparison essentially becomes nonsensical. Put a different way, if we believe the observations arise according to a certain data generating process, then we are encouraged to issue this process as our forecast. And in this sense, proper scoring rules discourage hedging. That is, we can't make some systematic change to our forecasts to result in a better score. And on top of this, since we typically compare forecasts based on average scores, we know by the definition of a proper scoring rule that this average score makes sense, or it is in some sense intuitive. This isn't necessarily the case for other scoring rules. So if we evaluate forecasts using scoring rules, we want these scoring rules to be proper. However, it's important to note that evaluation metrics still exist and can still be informative without being scoring rules. In particular, there are several evaluation metrics that evaluate forecasts not just for one forecast and observation, but simultaneously over multiple forecast cases. And we'll talk about a few of these later on. Because they don't evaluate forecasts just by one single forecast observation, they officially aren't scoring rules, and hence we can't really talk about these evaluation metrics being proper or not. But the argument is that when we use a scoring rule to evaluate forecasts, this scoring rule should be proper, otherwise the resulting comparison doesn't make much sense. And we can look at some examples of proper scoring rules. For example, suppose that we're interested in predicting a binary outcome that either occurs or doesn't occur, such as precipitation occurrence or the occurrence of an extreme weather event. And in this case, a probabilistic forecast is simply a probability that the event will or will not occur. And popular proper scoring rules in this case include the 0-1 score, the Breyer score, the log score, and so on. And all of these plots show on the x-axis the forecast probability, and on the y-axis the corresponding score. In red, in the case when the outcome doesn't occur, and in blue, when the outcome does occur. And we see that in all cases, essentially as our forecast probability moves away from 0 or 1, our forecast becomes worse and the score increases. And the only differences between the three scores are how exactly the score increases as our forecast becomes worse. And in particular, we can see that the log score penalizes very bad forecasts much more heavily than the Breyer score. And this raises an obvious question, namely, we have all of these different scoring rules, so what scoring rule should we use to evaluate our forecasts? And in general, there is no way to choose between different scoring rules. But in the binary case, we actually have a nice result that says every proper scoring rule to evaluate probabilistic forecasts of binary outcomes can be written as a combination of what we call elementary scores. And I won't talk about these elementary scores in detail here, but essentially what this means is that we can evaluate our forecasts using these elementary scores. We can plot this in a diagram, which is often called a Murphy diagram, and then we know that if one forecast performs better with respect to all of these elementary scores, then it performs better with respect to any proper scoring. And to some degree, this circumvents the choice of a scoring function or a scoring rule in practice. If we are instead interested in forecast univariate outcomes, such as temperature, wind speed, or precipitation amount at a certain location, then while there are many different proper scoring rules, in this case, the most popular in weather and climate applications is the continuous rank probability score, or CRPS. And I won't go into the technical details in much detail, but I include this expression here because it shows that when we have an ensemble forecast, several possible weather scenarios, then the CRPS can be written in quite a straightforward, simple formula. And in particular, when we have just one ensemble member, i.e. when our forecast is a point forecast, then the CRPS simplifies to the absolute error. And this partly explains why the CRPS is so commonly used in practical applications. In particular, we can use the CRPS to compare probabilistic forecasts and ensemble forecasts and point forecasts. So if we have, for example, weather forecasts from ensemble prediction systems, from statistical post-processing models, but also from deterministic weather models, we can compare all of these forecasts using the CRPS, which often isn't the case for other scoring rules. And on top of this, because the CRPS is simply the absolute error when we have a point forecast, we can say that the CRPS is on the same scale as the observations. For example, if we evaluate rainfall forecasts in millimeters, then the units of the CRPS will be millimeters as well, which somewhat helps with the interpretation of the score. The CRPS can also be extended to evaluate multivariate probabilistic forecasts. And I should stress here that multivariate doesn't necessarily mean doesn't mean that we have multiple weather variables, but it could also mean that we have one weather variable at multiple points in time and space. And this extension of the CRPS is called the energy score. And this energy score inherits some of the nice benefits of the CRPS. In particular, we can use the energy score to evaluate full predictive distributions, as well as ensemble forecasts, as well as point forecasts. And this is also very easy to implement when we have an ensemble forecast in practice. However, the energy score is sensitive to how well the forecast perform when predicting each of the individual variables. And one could argue that actually we already have univariate scoring rules that focus on this univariate performance, and hence the goal of these multivariate scoring rules, or multivariate evaluation more generally, should be to focus on the dependent structure, or that is, how well we capture the dependencies between these different variables. And as a result, the variogram score has been proposed as an alternative proper scoring rule that specifically focuses on this forecast dependent structure. In contrast to the energy score, the variogram score is insensitive to constant univariate biases. And again, whether or not this is a good thing depends on what exactly we want the scoring rule to evaluate. I should also mention that several other proper scoring rules exist for multivariate forecasts. For example, the log score is a very nice scoring rule in theory. However, in weather and climate applications, the log score has its limitation in that it cannot readily be applied to ensemble forecasts. The David-Sebastiani score is another popular scoring rule, but the David-Sebastiani score requires inverting, and if we have an ensemble forecast, also estimating a covariance matrix. And in many applications, this is no problem, but if we're working in very high-dimensional settings, for example, where you have spatial forecasts, then this covariance matrix estimation and inversion becomes quite impractical. And lastly, I want to mention the class of kernel scores, which essentially represents a very general, very appealing class of scoring rules that encompasses the energy score and the variogram score, and also other scoring rules that we've seen already, such as the Variety score and the CRPS. So these are popular examples of proper scoring rules when forecasting particular types of outcomes. An obvious question, though, is, well, we're often interested in particular in forecasting extreme outcomes. And in this case, how can we evaluate our forecasts? Now, a seemingly attractive approach would be to simply restrict attention only to instances where an extreme event occurs and evaluate only the forecasts corresponding to these extreme events. However, it turns out that this is not a very sensible strategy, and the reason for this is summarized quite nicely by this quote by Sebastian Werkler co-authors. And in particular, they say that if we restrict evaluation only to these instances where an extreme event occurs, then it becomes a worthwhile strategy to always predict that an extreme event will occur. But of course, such a forecast is not particularly useful in practice because it doesn't tell us when an extreme event will occur and when it won't. And this is often referred to as the forecast dilemma. And hence, to circumvent the forecast dilemma, several what we call weighted scoring rules have been proposed, which essentially take a conventional scoring rule and then they incorporate a weight function somehow into the score, and this weight function can then be chosen to assign more weight to particular outcomes. For example, if we're interested in threshold exceedances, then this weight function might be to 1 above some threshold and 0 otherwise, but more generally, we can use more flexible, more informative weight functions. And arguably the most well-known example of a weighted scoring rule is the threshold weighted CRPS, but many other weighted scoring rules also exist, and these have also been generalized to higher dimensions when working with multivariate forecasts. And we can also introduce weighted scoring functions, which allow us to target or emphasize particular outcomes when evaluating point forecasts. However, I should also say that proper scoring rules and also weighted scoring rules, they have some limitations when evaluating very extreme events, when we really get into extremes from a statistical point of view. And there have been some recent studies that show that scoring rules can't really just distinguish between two forecast distributions that have the same or have different tail behaviors. And this is still an open question. So this was scoring rules, but as I mentioned, several other forecast evaluation metrics also exist that are not scoring rules. And I argue that these are not scoring rules because they don't evaluate forecast performance. They've got a single forecast and observation, but rather they require multiple forecasts and observations to calculate this metric. And these metrics are more commonly employed when evaluating point forecasts. And I assume the reason for this is just that developing metrics to compare probabilistic forecasts is conceptually more difficult than when we're evaluating point forecasts, because we're comparing a probabilistic distribution to a single observation rather than to two possible outcomes. And I should also mention that while with proper scoring rules and consistent scoring functions, we have a nice theoretical framework that underlies these metrics, a lot of these, what I call aggregate evaluation metrics, which aren't proper scoring rules, they don't necessarily have some nice underlying theory. And so, in the sense that theoretical properties are generally less well understood, and that's not to say that these metrics can't be useful, but of course, if we want to interpret the results of a comparison based on these metrics, then it's important that we have an idea about what these metrics actually evaluate. And we can again look at some examples. So suppose that we're predicting binary outcomes again, and suppose that our forecasts are weight forecasts. So in this case, the outcome either occurs or doesn't occur, and the forecast either predicts that the event will occur or that it won't occur. And we can evaluate these forecasts by simply looking at the relative frequency that the event occurs and doesn't occur, given that we have forecast the event to occur and not occur. And we can store this information in a table. This is often called a contingency table or a confusion matrix. And then we can look at, for example, the number of true positives, false negatives, false positives, and so on. And we can use this to calculate metrics that summarize forecast performance. And many metrics have been proposed based on contingency tables. I'll just list a few of them here. For example, we could calculate the total proportion of forecasts that were correct, or given that we forecast that the event will occur, what proportion of these forecasts were correct, and so on. And as I said, this is really just a short summary, or short overview of possible metrics that have been introduced. But all of these metrics assess different aspects of forecast performance. So again, we can't say that one metric is in some sense better than another. We can think a bit about what properties we want these metrics to satisfy. But again, in order to interpret the results when we use these metrics for forecast comparison, it's important that we just understand what each metric is assessing and what its limitations are, and so on. So sticking with binary outcomes, but assuming now that the forecasts are probabilities. In this case, we can evaluate the forecast using ROC or ROC curves. And these ROC curves essentially take the probabilistic forecast and then they convert it to a binary classifier. And then they use these contingency table-based metrics and they plot the true positive rate against the false positive rate. And this is done for all possible binary classifiers. And if the binary classifier is perfect, then there should be a switch in which the true positive rate switches from 0 to 1 and vice versa. And so if we plot the false positive rate against the true positive rate, then we should have the plot essentially in the top left-hand corner. And this suggests that the binary classifier is very informative. We can then quantify the discriminative ability of the forecast using the area under the ROC curve, or the AUC. And again, I should mention that the AUC is not a scoring rule, in the sense that it can't be applied to individual forecasts and observations, but it is and still useful. It does still provide us with some information about how much information is contained in our forecast. That being said, it could be the case that we have a lot of information in the forecast, but this information is not being used correctly. And so in this sense, the AUC is not a scoring rule because it doesn't implicitly incorporate calibration or reliability of the forecast. And we'll come back to this later. And suppose that we're now forecasting univariate outcomes. Suppose again that we have a point forecast. Now in weather and climate forecasting, the very popular metric to evaluate these forecasts is the anomaly correlation coefficient. And you may have seen this plot before earlier in this course. The ACC is the correlation between forecast anomalies and observation anomalies. And again, I mentioned that this isn't a scoring rule or a scoring function because it can't be evaluated for one single forecast and observation. But this metric is still useful because we know that if this correlation is close to 1, then a large forecast, so a forecast that is larger than average, generally corresponds to an observation that is larger than average as well. And of course, this is intuitively a property that we want our forecast to satisfy. Sorry, our evaluation metrics to satisfy. And finally, consider the case where we want to forecast multiple variables simultaneously. And in particular, suppose that we have some spatial forecasting problem. Now, of course, we can calculate metrics univariately for each variable of interest, and then we can aggregate them or average them across all of the different variables. But this, of course, ignores the dependence between the different variables. And as an example of this, we consider wind speed forecast fields over Central Europe. So here, wind speed is measured in meters per second, and the more red values correspond to larger wind speeds. So we have the observation on the left, and then we have 3 point forecasts, forecast A, forecast B, and forecast C. We can ask ourselves which wind speed forecast is better. And clearly, just by looking at the forecast, we would say that forecast A gives a better forecast than forecast B and forecast C, because it somehow looks more realistic, it looks more close to the corresponding observation. However, if we only look at performance at each grid point separately, and then aggregate this across all grid points, then it could be the case that actually forecast A and B receive exactly the same score. The reason being that this metric is completely insensitive to the spatial structure of the dependence between the different grid points. In contrast, forecast C correctly predicts the dependence between the different grid points, but it has some constant bias in the forecast. And hence, if we were to use a multivariate evaluation metric that focuses only on this dependent structure, then forecast A and forecast C would probably receive the best score. And hence, it's not so trivial to think about what metric we should use to evaluate these spatial forecasts in practice. There is, however, a very large literature on spatial evaluation of point forecasts, and these evaluation methods are typically grouped into 4 or 5 categories. For example, we have neighborhood or fuzzy methods, which essentially average across multiple grid points or within a local neighborhood, and this somewhat relaxes the requirement that forecasts correctly get the space and time of an event, such as rainfall. We also have scale separation methods, which essentially decompose the forecasts into contributions from different scales, and then try to assess how good the forecasts are at each of these different scales. Feature-based approaches try to identify meaningful atmospheric features in the observations, and then they assess forecasts with respect to how well they can forecast these features. Field deformation methods try to measure how easy it would be to merge or transform the forecast field into the corresponding observation field. And distance measures are similar to what we've discussed already, where we're trying to measure some measure of closeness between the forecast fields and the corresponding observations. And of course, this is a very rough overview of these different methods. There have been a few review papers on spatial evaluation, and I encourage you to read these for more details. But I should also highlight that while spatial evaluation has received a lot of attention when evaluating point forecasts, there is much less literature on spatial evaluation methods when evaluating ensemble forecasts or probabilistic forecasts. The general approach is to either implement some neighborhood-based method, or we transform the forecasts so that they are something more low-dimensional, and then we can apply scoring rules such as the energy score and variogram score to these lower-dimensional options. So to summarize, we've argued that probabilistic forecasts can be ranked and compared using proper scoring rules. And we want our scoring rules to be proper because they incentivize us to issue what we call truthful predictions. And in practice, we would calculate the scoring rule over multiple forecast cases. We can calculate the average score, and we would then prefer the model, or the forecast model, with the lowest average score. And as I've argued, in practice, while we want our scoring rules to be proper, there is generally little reason to prefer one proper scoring rule to another. And implicitly, the scoring rules should somewhat encode our beliefs about what it is for a forecast to be good, but this will change depending on how we use the forecasts. And in this sense, the optimal scoring rule to use will change also on what exactly we want to evaluate and how we intend to use the forecasts afterwards. So this is for probabilistic forecasts. As I said, we can also evaluate point forecasts using scoring functions, and we want our scoring functions to be consistent, and this is essentially an analog of proper scoring rules for the point forecast case. That being said, several evaluation metrics exist, and they're useful when, even though they are not scoring rules. We looked at a couple of examples, such as rock curves and the area under the rock curve, as well as the anomaly correlation coefficient and metrics based on contingency tables. But in any case, it's obviously recommended that in practice we evaluate our forecasts using several metrics, because in doing so, we can essentially target different aspects of forecast performance or the forecast distributions, and this allows us to obtain a much more complete understanding of how the forecasts are behaving and how they are performing. And as I've argued multiple times, really the key of forecast evaluation is that we actually understand what our forecast evaluation metrics are evaluating, because if we don't, then a comparison with respect to these the resulting scores doesn't really make much sense, or at least we don't know how to interpret it. So we've compared two different forecasts using some evaluation metrics. However, even if we rank two different forecasts or multiple forecast models, then there's no guarantee that the forecast model that results in the best score or the best metric actually gives us good forecasts. And in particular, when we issue probabilistic forecasts, if we want these forecasts to be useful for things like decision making, then it's important that the forecasts are reliable or calibrated. And loosely speaking, we say forecasts are calibrated if they align somehow statistically with the corresponding observations. And there are many different ways to measure this alignment or to quantify calibration. But in practice, forecast calibration is typically assessed using diagnostic tools, in particular graphical diagnostic tools. And these diagnostic tools are useful because they not only allow us to assess whether our forecasts are calibrated, but we can also use these diagnostic tools to identify systematic biases in the forecasts. And we'll look at some examples in a minute. I should also mention that we discussed proper scoring rules already. Proper scoring rules implicitly evaluate forecast calibration, and we can make this explicit, this connection between forecast calibration and proper scoring rules explicit by looking at score decompositions. And I won't talk about score decompositions here, but I wanted to mention that they exist. So suppose that we're interested in predicting a binary outcome that either occurs or doesn't occur. And we're focusing here on probabilistic forecasts. Now, what does it mean for such a forecast to be calibrated? Well, if we say that it will, for example, rain tomorrow with probability 0.2, we generally say that our forecast is calibrated. If it does, then indeed rain tomorrow with probability 0.2. And of course, we want this to hold regardless of what forecast probability we issue. And this means that we can trust our forecast because if we say that an event will occur with a certain probability, then it does indeed occur with this probability. And we can assess this in practice by essentially plotting our forecast probability against the relative frequency that the event occurs given our forecast. So given a set of historical forecast observations, we can look at all of the cases where we issue a forecast close to 0.2, say, and then for all of these forecasts, we can calculate the relative frequency that the observation occurs given this forecast. We can then plot this forecast probability against the relative frequency, and if the forecast is calibrated, then these two should be roughly the same. And this is generally called a reliability diagram or a calibration curve in the machine language. So what does this reliability diagram look like? Well, on the x-axis, as I said, we typically have the forecast, and then on the y-axis, we have this relative frequency that the event occurs given our forecast. And in practice, of course, we typically need to estimate this relative frequency, and this might involve binning similar forecasts together or fitting some sort of model. But at least in theory, if our forecast is calibrated, then we should have a diagonal line suggesting that the forecasts are reliable. So if we have a diagonal line, then the forecasts are calibrated. But as I said, these diagnostic tools are useful because if the forecasts aren't calibrated, then we can often identify systematic biases that are present in the forecasts. For example, if our reliability diagram looks like this, then it suggests we have some positive bias in the forecast. For example, when f is equal to 0.5, then we can read off on our chart that the relative frequency that the event occurs given this forecast is roughly equal to 0.25. And this suggests that we are over-predicting the probability that the event occurs, again, suggesting we have some sort of positive bias. If we have the opposite shape reliability diagram, then it suggests the opposite bias, namely that we are under-predicting the probability that the event will occur, suggesting, again, we have some negative bias. And if we have S-shape or reverse S-shaped histograms, reliability diagrams, then we can also make conclusions about how confident we are in the prediction. For example, whether we are issuing forecasts close to 0 and 1 more often than we should. And so this was for binary outcomes. We can also look at measures of calibration for univariate outcomes. And in this case, several different notions of calibration exist. The most common notion is what we call probabilistic calibration. And probabilistic calibration essentially assesses whether observations resemble ensemble members on average. That is, whether we can interpret the observation as a kind of extra ensemble member on average. And this is typically assessed using rank histograms. However, I should note that many other notions of calibration also exist. Another popular notion is marginal calibration, which essentially assesses whether the forecast calibration is the same as the observed. Sorry, the forecast climatology is the same as the observed climatology. And this is particularly useful for things like climate simulations, where there's no direct correspondence between the simulated climate and the actual climate at any given time. But probabilistic calibration and marginal calibration are what we call unconditional notions of calibration. And it could be the case that on average we are calibrated, but if we look at forecasts in particular seasons or particular locations or for particular variables, then in each of these particular circumstances, the forecasts are miscalibrated, but these errors essentially cancel out over these different cases so that when we look at everything combined, the forecasts appear calibrated. And hence we additionally need to assess conditional notions of calibration, which essentially look at calibration conditional on these different forecast cases. But as I said, in weather and climate applications, the calibration of forecasts is typically assessed using rank histograms. And rank histograms take an ensemble forecast and an observation, and they essentially look at the position of the observation among the ensemble members. And then they calculate the rank of the observation when pooled among the ensemble. And if the observation and the ensemble members are exchangeable, at least on average, then the observation should be equally likely to take any rank within the ensemble. And as a result, if you plot a histogram of these ranks, then the resulting histogram should be approximately flat. But as with reliability diagrams, while these histograms not only allow us to evaluate whether or not the forecasts are calibrated, we can also use the shape of the histogram to identify systematic biases in the forecast. For example, if the observation is commonly below all ensemble members, then it often receives a rank of 1, possibly 2, and hence we would get this second histogram, where this is clearly not flat. And because we can tell from this histogram that the observation commonly is below all of the ensemble members, we can use this to deduce that the forecasts are biased, and in particular we have some positive bias. The ensemble members are always larger than the observations. And again, the opposite pattern suggests the opposite bias, namely negative bias. We can also use our rank histograms to identify systematic biases in the spread of the forecast distributions. For example, if we have a U-shaped histogram, then it suggests the observations are commonly either below or above all of the ensemble members, suggesting our forecasts aren't spread out enough, or they are underdispersed. And again, the opposite pattern suggests overdispersion. So these rank histograms are very commonly used to assess the calibration of ensemble forecasts in practice, but they assess the entire forecast distribution. And as I've argued earlier, often we're interested in particular on evaluating forecasts made for extreme events. But it turns out that rank histograms can actually be extended to assess the calibration of forecasts made for extremes. And these are often called conditional rank histograms. And these conditional rank histograms have exactly the same premise, but we're now comparing extreme observations to extreme ensemble members. But again, we can calculate the rank of these extreme observations among the extreme ensemble members, and we can then plot these ranks in a histogram over all of the cases where an extreme observation occurred. And if the histogram is flat, then it suggests the extreme observations are essentially plausible extreme ensemble members, and in this case we say the forecasts are tail calibrated. But again, we can use the shape of the histogram to identify systematic deficiencies or systematic biases in the forecasts. In particular, if extreme observations are always larger than the extreme ensemble members, then it suggests that the forecasts have too light a tail, the ensemble members aren't extreme enough, and in this case we get this middle histogram. And again, the opposite pattern suggests the opposite. If the ensemble members are too extreme, much more extreme than the observations, then the rank of the extreme observations when pooled among the extreme ensemble members will commonly be close to 1. And rank histograms can also be extended further to evaluate multivariate forecasts. And so to evaluate multivariate forecasts, as I said earlier, it's common to transform the multivariate forecasts and observations to univariate objects, and then we can assess the calibration of these univariate objects using established univariate calibration tools such as rank histograms. And the reason for doing this is that assessing, and in particular visualizing calibration in higher dimensions is much more difficult than assessing and visualizing calibration for univariate forecasts. And so typically how we evaluate the calibration of multivariate forecasts is to choose some sort of transformation function. This is often called a pre-rank function. And then we can apply this function to our forecasts and observations, and we essentially take our multivariate forecast and observations, and from this we get univariate forecast and observations for this transformed variable. And this transformation could, for example, resemble a univariate physical quantity. For example, if we have precipitation fields, then a relevant transformation function might be to look at the total precipitation across the entire field. So this is a univariate physical quantity. But of course, we can also use statistical or summary statistics, such as the mean or the variance, or some measure of dependence among the multiple variables. And of course, in practice, we shouldn't just use one transformation function or pre-rank function. If we really want to understand how our forecasts perform in different scenarios, then we should choose multiple transformation functions and evaluate the calibration with respect to all of these transformation functions to see when our forecasts are calibrated and when they're not. So then, having transformed the forecasts and the observations to univariate things, we can then assess the calibration of these forecasts using univariate rank histograms. And these are often called multivariate rank histograms because they show the rank of the transformed multivariate observation among the transformed multivariate ensemble members. But the interpretation of the histograms is the same as before. If we have a flat histogram, then it suggests the forecasts are calibrated when predicting this transformed variable, and we can again use the shape of the histogram to identify systematic biases or deficiencies in the forecasts. And again, the only change in the interpretation is that we're not predicting the entire multivariate observation, but we're restricting attention to this transformed variable. So to summarize, calibration is really an essential or fundamental property that we want probabilistic forecasts to satisfy. It essentially means that we can take our forecasts at face value, which is important when we use these forecasts for things like decision-making and risk assessment. And it's often stated that the goal of probabilistic forecasting is to issue forecasts that are as sharp as possible, subject to being calibrated. And so in this sense, calibration is really a property that we want our forecasts, so we need our forecast to satisfy. And when we're forecasting binary outcomes, we can assess the calibration of our forecasts using reliability diagrams or calibration curves. And when we extend this to univariate outcomes, we can assess the calibration using rank histograms. And as I've said, these rank histograms can be extended further to focus on extreme events, and they can also be used to derive multivariate rank histograms to assess the calibration of multivariate ensemble forecasts. And these graphical diagnostic tools are particularly useful because, as I've said, they not only allow us to assess the calibration or assess whether our forecasts are calibrated or not, but if the forecasts aren't calibrated, we can also use the shape of these diagnostic tools to identify systematic biases in the forecast. For example, whether there is some positive bias in the forecast, some negative bias, or whether the forecasts are overconfident or underconfident. And of course, the idea is that these graphical diagnostic tools therefore provide us with more information regarding forecast performance. And if we identify that there is some systematic bias in the forecasts, then we can use this information to try to remove these biases in the future, resulting in a better, more calibrated forecast system. So, as I said, this is what I wanted to talk about regarding the statistical methodology of evaluation. In practice, how do we evaluate forecasts? Well, we can adopt the methods that we've just discussed, but at the moment there is extensive ongoing work trying to compare AI weather prediction models to more traditional numerical weather prediction models. And a question that often comes up is, how can we fairly compare AI weather models and numerical weather models? And so if we look at some examples of these two different types of models, we see that actually overall AI models are fairly consistent with physical models. They capture the large-scale trends. But there are several challenges that arise when trying to compare these forecasts. And I'll list a few of these challenges here. I should state that these aren't all challenges that arise, but there are at least some problems that often come up. For example, AI weather prediction models are data-driven, and therefore they are trained to optimize a loss function, and commonly they are trained to optimize the mean squared error or the root mean squared error. And this means that if we evaluate forecasts using the root mean squared error, then these AI weather models essentially have some inherent advantage because they are trained to optimize this as their loss function, whereas numerical weather prediction models, of course, are built based on numerical or physical laws. And it should also be said that, as we've argued already, if we evaluate the mean squared error over multiple grid points and then average across these grid points, then this doesn't necessarily give us realistic forecast fields. And in particular, the mean squared error is consistent for the mean functional, and hence we tend to get smoother forecast fields when we use this as a loss function, and hence it's also perhaps not the most appropriate loss function to use, scoring function to use when evaluating forecasts. On top of this, we look at different AI weather prediction models. These models are often trained using different data sets. For example, many of them are trained using ERA5 reanalysis fields. Others are trained using operational IFS analysis fields. But of course, in any case, if we evaluate our forecasts using one of these data sets, the models that have been trained using this as the observations, will generally perform better with respect to these observations. And so the ground truth that is used in evaluation is not always independent of the ground truth that is used in from training. And of course, in both cases, the analysis and reanalysis fields are not perfect. We know that they are not the exact weather, but they are just the best guess we have of the weather. And so there is, of course, some uncertainty in the observations, and we additionally need to account for this if we can. And a further problem, of course, is that while a lot of AI weather models are trained using the Area 5 reanalysis, these reanalyses generally aren't available at the time of forecasting, and so they use information from the future. And again, this leads to a kind of biased comparison between numerical weather models that don't have access to this model when they run. On top of this, AI weather prediction models typically have different configurations. As a particular example, models that typically run at different spatial resolutions, and hence if we want to compare these forecasts to the observations, we often need to either downscale the forecasts onto a consistent grid, or more generally, we just need to make sure that the forecasts are comparable. And this is true not just for AI weather forecasts, of course, but also for traditional numerical weather prediction models. But regardless of what pre-processing we do, this pre-processing can bias the results because it could deteriorate forecast performance or even improve it in some cases. And finally, in most studies, comparisons of AI weather prediction models and numerical weather prediction models have focused on the raw model output. However, operational weather forecasts typically aren't generated just from numerical weather prediction or the raw NWP output, but rather these models often undergo some form of statistical post-processing to remove systematic biases in the forecast. And studies have also shown that AI forecasts can benefit from post-processing. And hence, if these operational forecasts aren't the raw model output, how informative is a comparison of these raw model outputs? Or is it more informative to evaluate the post-process forecasts after this full chain of post-processing? And these are still open questions, but several potential solutions have been proposed, and I'll talk about a few of these here. Firstly, of course, if you want to compare AI and numerical weather prediction models, then it makes sense to use the same data for training these two models. But on top of this, if AI weather prediction models are trained to optimize a certain loss function, then they still have some sort of bias when evaluated using this loss function. And hence several studies have proposed post-processing the numerical weather prediction models and the AI weather prediction models. So from deterministic forecasts, we can then get probabilistic forecasts, and then we can evaluate these probabilistic forecasts using probabilistic evaluation metrics such as proper scorings. And the motivation for doing this is that post-processing essentially removes any biases that are induced by the choice of loss function and the data. And of course, as I mentioned, because operational forecasts typically undergo some form of post-processing, the resulting score is representative of operational forecast performance. And finally, in order to try to progress the literature on comparisons of AI weather prediction and numerical weather prediction models, several benchmarking frameworks have been introduced. Which the most well-known are WeatherBench and WeatherBench 2 and WeatherBench X. There are also other examples such as ChaosBench, StationBench, and more recently Extreme WeatherBench. And all of these benchmarking frameworks try to provide observations and forecasts from state-of-the-art models in a kind of standardized form. And this is particularly useful for evaluation because it allows us to compare these different models in a kind of standardized way. And I think such benchmarking frameworks are really incredibly important in practice because we've seen already that results from such comparisons based on these benchmarking studies has been used to create a kind of feedback loop, which allows us to then improve our models further in the future. So to conclude, I've argued that forecast evaluation plays an integral role when developing forecasts, in particular weather forecasts. And the general goal of forecast evaluation is to provide us with information that we can use to learn how our forecasts behave and how they perform. And of course, the idea then is that we can use this information to try to improve our forecasts in the future. We can compare two different forecasts using what we call evaluation metrics, and these evaluation metrics condense forecast performance into a single numerical value with which we can then rank and compare competing forecasts. When we have point forecasts, then we argue these evaluation metrics should often be based on consistent scoring functions, and when we have probabilistic forecasts, we can use proper scoring rules. But it's also important to mention that other evaluation metrics exist that don't fall into the scoring rule or scoring function framework. And we looked at some examples, for example, the anomaly correlation coefficient, ROC curves, or metrics based on contingency tables. And these aren't scoring rules or scoring functions because they can't be evaluated using just one forecast and observation. And while their theoretical properties are therefore slightly less well understood, they can still provide us with useful information. But even if we have some evaluation metric and we compare two forecasts using this metric, it may be the case that the forecast with the best metric doesn't necessarily result in good or calibrated forecasts. And in that sense, we additionally need to assess whether probabilistic forecasts are calibrated or reliable. And this is typically done using graphical diagnostic tools such as reliability diagrams and rank histograms. And so calibrated forecasts are required for effective decision making, and these graphical diagnostic tools are particularly useful because they not only provide us with information regarding whether the forecast is calibrated or not, but we can also use them to identify systematic biases and systematic deficiencies in the forecast. And again, we can then use this information to improve future predictions. So to summarize, there is no correct way to evaluate forecasts, and the most important thing is that we actually understand what our evaluation metrics or our diagnostic tools are assessing. And in particular, we have lots of different methods to assess different aspects of forecast performance, and it's always recommended that we employ multiple forecast evaluation tools to really gain a more complete, comprehensive understanding of how forecasts behave and perform. Thank you.